Hello, everybody. Thank you for coming to my talk. I know there are many other choices, so I appreciate you coming. My name is Shavit, and today I want to talk to you about what I talk when I talk about cross-platform development. Now, I don't know if any of you recognize this, but I stole this from Haruki Murakami's book, What I Talk About When I Talk About Running, which is a book about running. And he actually stole it from Raymond Carver from another book. So I decided I'm going to continue that tradition. Now, a little bit about me. I'm a software architect. I've been working in writing computer vision and machine learning software for about 20 years. I've worked for multiple companies. At the moment, I'm working as a consultant with small companies and large companies. And I also started the Core C++ users group in Israel. And this talk is based on a blog post I wrote on my blog. You're welcome to go and check it out over there. And I usually tweet it any interesting things I'm going to talk about. Now, as a consultant, doing a lot of very deep and core technology and algorithms for, as I said, computer vision, machine learning, many of my clients need to target multiple systems. And in that capacity, I often come across the need to work across multiple platforms. And before we talk about how we do it and how we structure our code, let's think about what cross-platform actually means. And if I try to go from the lowest level up to the higher levels, then possible platforms that we might need to target our applications to include anything from custom-designed hardware through embedded systems. And even today, embedded systems mean it's a very wide variety of processors, from your washing machines all the way to basically smartphones. Of course, we have mobile devices of various different hardwares and different softwares, different operating systems, entire platforms and ecosystems. On the desktop, we have Windows machines, we have Linux machines, we have Mac OS machines, and many other different types of operating systems that our system might need to target. But also, there are newer, more modern platforms which didn't even exist up until about 10 or 15 years ago. And I did some browser plugins. These are no longer a technology that's actually used in many places, but still JavaScript is the de facto language running inside browsers, and WebAssembly is now taking that place, and we're actually going to see a little bit about that at the end of the talk. And of course, some more platforms that we need to target are cloud servers. These are not desktops. This is not a single machine. This is a huge racks running somewhere that we might need to target. And each one of these platforms has its own different types of constraints and different types of operating conditions. But even if we can go beyond that. We can talk about software running in your cars. Some of you know there's modern cars actually have their own operating systems and their own constraints. IoT, the Internet of Things. We have these tiny connected devices that need to interact with the world. They sample the world, they sense the world, they interact with the world, they affect the world. And robots. If maybe some of you have heard about ROS, the robot operating system, again, allows us to abstract away a lot of the particulars of particular robots, but again, we might need to target these systems, and we might need to write software that runs on different robots interacting with different ecosystems. And of course, we might need to target CPUs or GPUs or other type of heterogeneous computing devices. So all of these are different platforms, each with potentially very different requirements, very different constraints, very different ecosystems. And this raises the question, how do you manage your development stack? How you manage your code base? How do you maintain your system while targeting multiple platforms? And I will be the first to say it's extremely rare that you actually need to target all of these systems. But I have, in fact, had to target many subsets of these in different projects. And what I want to talk about today is really the lessons that I've learned from trying to manage this type of architecture. Now, I will say that my talk, most of the examples, although not of all of the code I will show, is going to be in C or C++. But I think the lessons here are much more general and can be applied to many other languages. So if C++ is not your cup of tea, I think you still find some of these things interesting. But I will say that I think that C and C++ are probably the only viable languages for true cross-platform development. And by the end of this talk, if you're resisting the urge to raise your hand and argue, just hold it inside and let's talk at the end of, when I finish, okay? Now, I'm not going to talk about, when I say cross-platform, I don't mean things like frameworks that abstract away some of the underlying platform-specific code. And I don't mean things like the JVM. Because everything I'm going to say actually applies to the people who implement these frameworks. And it applies to the people who implement some of these JVMs. So bear with me. Now, when we come to we go to many popular websites to read about our platforms. It could be, I don't know how many people are still frequently go to code project, but MSDN databases, the Qt. You can go to see some Android examples, iOS examples, and some other similar websites. A lot of the code samples are there mostly to show how to use some SDK, and they frequently mix a lot of things which we as developers or as architects or as people are trying to write proper software that's going to be maintainable for multiple years. It's not very helpful beside the particular line of SDK that you want to use, because the code is usually spaghetti code mixing a lot of different aspects of whatever your actual system is trying to do. It's generally not portable. It's very difficult to unit test and bug prone. And one more aspect, which is not generally considered when you're talking about software development, but it is extremely important, is the mixing of skills. An iOS app developer does not have the same skill set as an algorithm developer. An Android developer doesn't have the same skill set as a web developer. And when we have an organization, even if you're a team leader inside a larger organization, you want to leverage the people that you work with to the maximum and maximize their ability to affect your product. And I'm going to show how this works. And now, we can go even beyond that. When we're trying to write some kind of dynamic library, maybe DLLs or SO files or any kind of executable that has module boundaries, when we try to pass beyond these boundaries, we have whole issues related to error handling, because exception throw for DLL generally leads to a termination of the program. We have to think about those kinds of things and how we handle these things in such a way that we can make our software more correct and more robust. Now, I whimsically call the method that I came up with, I call it the Salami Method, because it's all about slicing your requirements so thin that everything is very transparent. Because I'm going to show you many aspects of the method, and the idea is to expose everything in such a way that you understand the concepts, and everything builds easier. It's possible to test everything separately and independently. It's easier to debug, easier to manage, and of course, easier to maintain. Right, so this slide is going to go with us throughout the talk. It's going to be in the corner, and we can always reference it. And this is really the gist of the talk. So if you don't remember everything, but you can just print out this slide and put it on your cubicle wall. And this can be more or less summarize everything I'm going to say. The system has multiple layers, and I will go over each one of these layers and explain some of the aspects and why I made these separations, and I'll explain some of them, the terms that I'm using here. But the important thing to remember is that most of the system you'll write do not actually implement all of these layers as separate classes or separate actual code implementations. However, all of these aspects still remain in your code. They never go away. So even if you decide to make some of your layers thicker, as it were, these aspects still remain, and they're still there behind the code, either implicitly or explicitly. So we always have to keep these in mind. And I'm going to talk about how we unit test each one, or test in general, each one of these layers, and why it's structured in such a way. Right. So the main benefits of slicing our architecture in this way are essentially that we want to try and avoid duplication. We want to avoid re-implementing things. I've worked with teams where they had an iOS developer, a whole team of iOS developers, and a whole team of Android developers, and they're basically implementing exactly the same thing. I will say that things like front end and UI and GUI generally work better if they are implemented independently for each platform, and that's something that we can't avoid. But I think everything behind that superficial layer that the user actually sees that runs on whatever platform should be abstracted into some kind of a common interface. And once we have this ability to extract, we can test it separately. And we can have transparency and, as I said, consistency, because once the business logic is separated away, our apps, we won't have different bugs on different platforms related to things like business logic. And of course, if Microsoft does finally manage to get millions of people to buy its Windows Phone operating system, then we're essentially ready. Just get some Windows Phone developer to add the final touches, and suddenly you're in the Windows App Store, right? Because we're new platform ready, because most of the work has already been done. And as I said, developer skills, we have different people with different skills that we hired for different types of roles, and we don't want them having to debug somebody else's code where they don't specialize. And of course, making refactoring easy. So let's start. I'm sure you're all anxious to see where I'm going with this. And at our bottom layer, at the core of our system, is it's the cross-platform C++ core, right? So actually, I will say as an aside, I'm not going to talk. As I said, I'm not going to talk about front-end related UI stuff, because that's usually very platform specific. What I'm talking about is when we have to build some kind of system which has some logic or some algorithms, or maybe a compute phase, or all kinds of things of those sort. And there, C++ is your go-to language when you want to target multiple platforms. And at the heart sits the cross-platform C++ core. This is where the business logic resides. This is where we can put proprietary code, our IP, if we want to patent some of these concepts. And this is where we use idiomatic C++, for example, or whatever language you're using, all the design patterns and proper hierarchies of classes. And the focus when you're writing this beautiful system is, of course, on solid, maintainable, well-designed architecture, something that your team can maintain throughout the years and upgrade and refactor and work on it, regardless of where the actual code is going to be run. Generally, this is you would have some kind of cross-platform build system, maybe write it as a static library, and unit testing. The testing that you would do at this point is generally unit testing and functional testing, which goes to check things like the business logic. You want to make sure that you're up to spec, the specification that your client gave you, or the specification that the development team committed to. So the second layer that I at least often encountered, and I do point out here, and we can see at the top right corner that we just rose one level up. I call it the cross-platform public C++ interface, or ZAPI for short. This is the public C++ core API. Now, this is a slightly subtle distinction from what we had before. But in this case, the focus of what we want to expose to whoever is going to use the service is the focus of the design or the architecture of this API. This is where we're starting to think in API design and not necessarily class diagrams or proper design patterns. We're starting to think about our service users. And this is the point where we do that. And by separating it from the underlying layer, we can keep this separation clear. And whenever we have we don't need to make a lot of compromises on either side. Another important thing to think about at this layer is things related to initialization and shutdown of your system. Things like lifetime management. How do we handle sessions? How do we handle serialization, reading configuration files? All these things that might not be relevant in one particular platform, let's say a server that boots once a year or once every several months, but are extremely important when you have to run on a cell phone or in the browser. So this is a point where you must think about these things. Another thing that you can do at this point is to hide proprietary code. Let's say we're a different team, or this might be something that your client is receiving. So they're only getting binaries and a bunch of interface files. In C++, it would be header files. And we might not expose that we're using some internal proprietary libraries. C++20 is going to have modules, and this is, in many aspects, this is a classic poster child for module, the type of things that would go in module, which are exported interfaces for our class. And at this point, the type of testing that we do is mocking and unit testing of the API itself. So we don't actually need to test the business logic. We don't need to run unit tests at this point because we already did that at the previous layer. And we know that works. So at this point, we only need to test the new API. And one example that I did have a client some time ago, they didn't want to have Boost inside their iOS app. So this is the place where we could replace some of the Boost classes with some other interfaces that are important, that are alternatives. And I generally, if my C++ file is called core CPP, I generally would call this core API CPP. And as I said before, for many small projects, this might not actually be a layer that's explicitly separate from the layer underneath it. So it might be part of the same API that the core library that's underneath. However, these aspects still remain. They just might happen to be exactly the same design as we had before. Right. So since we're talking about layers, this is the point where no business logic must go beyond. Because at this point, we're going to start shedding our cross-platform ability and starting to somehow adjust to whatever platforms we are targeting. And that means that we're getting a bifurcation. We're starting to spread out. And if any business logic leaks out, then it means we're going to have multiple implementations, which means different bugs, different versions of the same logic, both implemented multiple times and maybe generating different bugs. Right? So no business logic beyond this point. And our third layer is what I call the cross-platform public C interface, or the XCAPI, if you will. Because I think we mentioned this yesterday at the user group. The true lingua franca, the true language, common language of computing is C. There is no hardware platform, at least these days, that you can find that doesn't implement a C compiler. Every vendor knows that if it brings out a new chip, it must come with a C compiler. And generally, it doesn't come with anything else besides the C compiler. So C is the lowest common denominator of all programming languages. And that's why we have to understand, and in order to allow us to interact with basically any computing platform on the planet, we often need to create a C interface. And however, I'm not gonna tell you and preach to you to start writing in C, because I think that's counterproductive. And remember, we're working in layers, so we already did the business logic, and we already defined the way our service is going to be used. So all we really need to do is create some kind of thin C wrapper around our cross-platform API, which exposes the same API. And at this point, because of C's simple ABI is the application binary interface. It's what allows us to link between different binaries. All we need to do, when we're writing functions, we define extern C and create basically C linking functions. We can do things like portable conversions, where if we had used many C++ classes, for example, we might consider using some weaker types at this point, and going back to some kind of some C primitives. And at this point, we also need to think about lifetime management from a C point of view. So we might use some kind of global variables like or singletons to inside our opaque binary. But we can also use opaque handles and many other techniques used in C for decades. And this is the point where we actually need to think about these things. There are some technical issues, like C doesn't support overloaded functions with the same name, so we might need to rename or generate multiple differently named functions for the same C++ function. And again, at this point, we can do some maybe mocking and unit testing the C API itself, but we don't actually need to test everything underneath. So everything is nicely separated. I generally just, I call these files, I would call it core C API. Actually, I call it CPP. It could be .c, of course. And at the point where we're actually implementing these functions, it's like I have this tip here from the C wrapper, is that we don't want to leave the safety of strong types. There's some, Bjorn is giving multiple talks about strong types, and C++, this is one of its big fortes. And although we're exposing a C API with some very low-level types, or you could say weak types, inside our implementation, nothing, as long as we made extern C, we can still use higher level and stronger types, things like std span, std string view, and other similar types. And I'll show you an example of what I mean. So let's say we have the 4 functions from our 4 C functions that are basically going to wrap some kind of C++ API, which we'll see in a second. It's wrapped inside an extern C. That means that the linker is going to generate a simple C API for these guys. We have 2 functions, init from file name and init from count. And in the C, they're both called init, but again, I said C doesn't have, you can't overload at the same name, so I separated them into 2 differently named functions. We have a function called process buffer, and some other, the last one is ready. Very straightforward. And one nice thing, if maybe the keen observer noticed, is that I'm actually using std string in the first function, which is a C++ class. It's not really a C function. So I like to think of C, when we do extern C, it means like air quotes. It's not exactly C. It doesn't have to be exactly C, because not all the systems that you might need to target require specifically a C API, but it's usually it's very convenient to work with standalone functions instead of a full-blown object-oriented class or object. And I'll show an example regarding this in just a second. So one implementation that I might have for these 4 functions, in this case, I'm just using a global foo session. It's going to reside in the, let's say this is some kind of DLL, so this is it's a global object. We don't expect to have more than one. And but as I said, in other situations, you might want to use opaque pointers and other mechanisms or maybe unique pointer or some kind of optional if we don't have a default initialization. And as you can see, the 2 init functions are actually calling the same 2 different methods called init on the session object. And and if we look at process buffer, this is what I meant before. The implementation, although the API of the function uses a low level, it uses a pointer and a size, the moment I actually come to use it, I'm going to immediately lift the type into a much safer STD span in this example. So nothing prevents us from trying to lift our types for safety and to stronger types the moment we can. Oh, by the way, please ask questions as I'm going through because I feel more comfortable knowing more people understand.
It means that for the C API, just for the first function, it has to see the character pointer.
No, specifically regarding the first function, I put that std string there intentionally because I was more, in that context, I wanted to show an example of not really requiring an actual C code. But if you really must use C, for example, like linking to some other kind of binding to some third party, to another language, then you would actually need a car star.
So you're not getting any error warning if you make an interface that's not
Well, I can any C code will compile in C++ code. So you remember it was called _C_API.cpp. So say I can compile this. This will work fine in a C++ compiler with the extern C linking protocol. But yeah. Question? Yeah.
What is the benefit of C linkage if you're only
Sorry, you have to speak out louder.
what is the benefit of C linkage if you're only going to use it with C++?
The question was what the benefit of C linkage if I'm only going to use it in C++? Well, the benefit of C linkage is mainly for the cases where you need C linkage. So I'm just saying, I'm talking about aspects of a particular layer. So this is not necessarily something that you would need in every system. You really have to decide whichever platforms you're targeting. So some systems you might, a C linkage is required. And in that case, of course, you won't use std string. Now, in this case, for example, you want to create a DLL for Windows. Then DLL doesn't, it's a C interface. I'm not going to talk about COM, so it's basically a C interface, but you can do some of the conversions. You'll see in a moment. You know what? Hold that thought, because I'm going to talk about it. And this is really the second thing that I want to get to. Right. So we're halfway through. And I want to summarize and emphasize a few of the things what we've seen. So on our bottom layer, we have our cross-platform C++ core, the code we all love and enjoy writing and playing around with. And as you can see, the second layer doesn't actually extend all the way to the end, because sometimes your C API might interact directly with your code, with your C++ code. For example, as I said, sometimes you don't actually implement two separate bottom layers. They might be the same because the interfaces and the kind of service you're providing just happens to provide the same kind of interface. On the other hand, when we look at our third layer, we see that it also doesn't extend all the way to the end. And you might think, okay, why is that? And the reason is because not all target systems need a C API. For example, just last week, I needed to bind some C++ code to create Python bindings. And there are some nice libraries like Boost Python or PyBind 11, which allows me to, and I'll talk about it in just a moment, but they allow me to interact directly with the C++ code. Another example is C++ code generally compiles fine under Objective-C in iOS. So often there is no need for this extra layer of exposing a C API. And that's why the third layer doesn't extend all the way to the end, because we do feel that we can expose some of these things to our target host. But if you're targeting both iOS and Android, for example, then your iOS might interact directly with the C++ code, but the Android Java, and we're going to see an example of that in a moment, does actually have to go through multiple layers until we can actually expose functionality. So At this point, we're reaching a second boundary, and this is the cross-platform boundary. Up until now, we were talking about cross-platform code. At the beginning, it was C++ code, which could build on any system. And then we went to a public API where we could maybe deliver some binaries, but the API was still cross-platform. And then we went to C, which we already saw is basically the cross-platform language. But now, having crossed the business logic boundary, we reach the cross-platform boundary. And at this point, there's no more cross-platform, and we have to start thinking about platform-specific code. And this is where we reach the boundary interface layer. This is where we're starting to, the skills and the type of development we're doing and the efforts and the time we spend with our project starts bifurcating into multiple platforms, multiple domains, maybe multiple code bases. And we have different people working on it. This is the layer, and this is exactly to answer your question. This is where we're thinking about things like conversions of data, because not all platforms support the same type of data. For example, JavaScript only knows doubles, if I'm correct, regarding numbers. But maybe our C++ code uses 8-bit integers. We have to think about conversions and types at this point. We have to think about other constraints of the system. We have to think about how we, different conventions for working with the code, and we'll see some example in a moment. And this layer, regardless of everything I just said, is also an excellent place to put platform-specific logging. Because let's say on Android, you have special logging facilities, and on a server running in the cloud, they are completely different. And we couldn't actually use them or set them up, configure them before, because we had everything was cross-platform. This is the place where we can hook in, maybe through some kind of abstracted interface, this platform-specific logging to generate the particular logging statements on each of the platforms. This is also where we see the module boundaries. So if you remember, the first function I had before took an std string, and I said that's not really an issue, because when I'm going to write a DLL, this is where I'm going to do the DLL, Windows DLL related code, and I'll show, I think the next slide shows an example. A big question mark is how you test this layer. I think I have an open Stack Overflow question from maybe 5 or 6 years ago. How can I actually test J&I code with a unit testing framework that doesn't need to run on the phone? And I've never received a satisfactory answer. So if you know how to test this layer to be sufficiently convinced that it does what it does, then do let me know. I'll be happy to hear about it. The naming convention I use for my files are just like this layer, they're platform specific. So I might have something called Core C API DLL or Core C API JNI or anything else, maybe C# or anything else. And let's continue the example that we've seen before. In this case, in this example, we're going to create a DLL, a Windows DLL, for example. So Windows DLL has particular it has its own conventions, the way you introduce interfaces, the prototypes of the functions. So this is where we use the DLL export macro, which gets substituted for some kind of built-ins like __ DLL import or export. The names of the functions, since we don't want to pollute the names, but we have to prefix them with an extra foo session, for example, to give them longer names. And note the first line, exactly what we were talking about before. Here I'm taking the LPC_str, which is a Windows DLL function, pointer to a character string. So this is where we see really platform-specific code targeted at this particular platform that we're talking about. And it's OK. At this layer, it's fine, and the guy or the developer who's going to write this they're Windows developers. They know what they're doing. This is where they can make sure everything works as expected. And the implementation would actually be, again, it's extremely thin. There is very little real code going on here. If we look at it appears like a very massive chunk of code on the screen, but in fact, it's there's very little non-repetitive code. So the first function, if we look at it just calls our C function, the global C function called init from file name, with the lpc_str file name variable, and Windows automatically converts that to std string, or well, to char star, which std string can accept. So there's automatic conversion to std string. The rest happen. They're basically kind of trampoline functions. We're not doing much here, but we are exposing a particular interface, which is targeted at DLLs. And one more thing that's extremely important for me to emphasize here is that, remember, this is the boundary interface layer. What does boundary mean? It means it's a module boundary. We're going to cross into some unknown domain where this DLL is going to run. And as I mentioned at the beginning, if an exception is thrown somewhere inside my code, all hell breaks loose. Probably the DLL crashes, the application crashes, the computer crashes, right? The spaceship crashes. So this is the point where we try the most to make sure that nothing happens, and that's why I'm using the function block, function try block here, and you can see I'm basically catching any exceptions. So even if the code does say, yeah, we're exception safe, or we're going to catch everything inside, I'm just going to put these here just in case, because if we catch them, let's say I can return false, and that means the function didn't work, right? So this is a point where we can add an extra layer of protection because we understand that this is module boundary. Right, so now we're going to do exactly the same thing for the same interface, but for Android. And because remember, this is this is platform-specific code. We have just passed the cross-platform boundary. So in this example, and again, if you've never seen Android code, it might appear a bit daunting, but most of it is boilerplate code. Oh, and by the way, I never said this is going to be fun or elegant. All I'm trying to help you guys do, and help myself do when I set this up, is make it more manageable and more transparent. So JNI code might appear very ugly and very verbose, but what you're going to do, you have to target your platform. So in this case, JNI really is just kind of a DLL for targeting Android. So at this point, we can include all the Android-related files like jni.h, android/log.h, and all our functions have to start with this JNI export prefix macro, and then we have to use the Android-related types called JBoolean, for example, or a JString. Now, if you've ever done Android or JNI in general, you have to pass, every function needs to, the first two arguments are the JVM environment and some kind of thing called the JObject, this. But this is a keyword, so they use the this. And again, what we're going to do is call the C interface. So that C interface that we implemented really makes it very, very easy to implement all of these functions in a very, very thin way. One of the things that kind of complicate life is that in Java or in JNI code, because we're in the C++ side, we still have to manually manage some of these, some of the resources. So in this example, I'm using a small library. There's some utilities that I wrote, just mostly to make the code more concise. So for example, to get the file name string, that JString type, really, what it does underneath, it goes to the JVM and fetches some kind of character array, which we actually need to manage and deallocate manually because we're not part of the virtual machine. So I have this GenI util get string, which handles all of that for me. And similarly, I have some kind of exception handler object, which I can call in case an exception is thrown. And that actually, one of the things, the ways I implemented is why I actually generate an exception on the JVM itself and translate the C++ exception into the JVM, into a Java JVM exception that's going to pop up on the client side. So this is an excellent place to do those kinds of nasty platform-specific things without polluting. Think about adding all of this platform-specific mess into where we also have our program logic. So this is what we're trying to prevent. Now, at this point, as we said, we were at the wall, we were at the boundary. We're not in Kansas anymore, okay? So now we get to the native import layer. This is literally running on the target platform. So now there's no more C, there's no more C++. There's no more platform-specific C++ or C APIs. Now we're running literally in another world. This might be on the device. It could be different hardware, different operating system. And very often, it's a completely different language. So at this point, we can't use our C++ foo anymore. We have to think about the native language of that particular platform. And to think what I ironically call the native interface, because the word native is very often used in two completely opposite meanings. Because if you think of the browser, then JavaScript is the native browser language, and if you think of an iOS, then maybe Objective-C or Swift are the native languages, and Java is the native Android language. But each of these languages, when they try to call a DLL function, they call it, this is our native interface. So at this layer, we're going to use the native interface, which means the interface on that particular platform that allows us to interact with our C++ exported functions. And at this point, our functions, since they were essentially C-like functions, we're going to have to interact with, and because these native interfaces are generally low level, this is what we must use at this point. And the kind of testing we do here is the target integration testing. So we just want to make sure everything works as we expect after the integration. And of course, the file name extensions, as you can see, we're not using C++ anymore. So it might be a JavaScript file, it might be a C# or Java or anything, wherever we're trying to target. Now let's see, this is a very simple example of using the native interface in Java. And most of it is basically repeating the same names with the proper convention of the native interface for Java. So we use, it's a system load library, and we give the name maybe of the DLL, public static native boolean. And the names of the functions, if you notice, they don't have the prefix of foo session because JNI. That's just how it works. Oops. And the classes, these are what we got passed down into the C interface. Of course, the code for C# would be almost identical to this one. And again, this is Java code. We're not in C++ land anymore.
But maybe means that we have to make two libraries 32-bit, 64-bit, right? Because Java doesn't care about the underlying DLL. Since you have a C interface.
Yeah, the question is if we need to make multiple libraries, for example, 32-bit and 64-bit, and the answer is yes. But that's a platform-specific decision we had to make at the previous layer. When we actually generated those, whatever tool chain you're using to generate, for example, JNI, this is the kind of shared object that your Java code is going to have to know how to load. And the last layer that we need to think about when we're writing our application is what I call the interface wrappers. And in our diagram, we'll see that in a moment. It's a rather small part of our hierarchy, but I find it extremely important because it gives the developers who are working within these particular platforms something that feels right for them. Right? It gives them the same type of abstractions that they're used to within their so-called native ecosystem. And let's see an example. So this is just I'm not me waving my hands, and this is a slightly different example from Android or Java. So say I have this DLL that I wrote. It's called Native Face Detector. And I'm using the native interface of system load library to load this DLL. And it has some kind of one function called get face center point. And this is, remember, this is just a binary interface into a DLL that's using a C ABI. So we can't use any classes here. And as you can see, it's returning an array of floats. Maybe these are the coordinates of the center of the face of which pixel inside the image contains the face, or maybe it. But this isn't a natural. It's unnatural for a Java developer to think about arrays of numbers instead of coordinates, instead of pixels. So what we want to do is to take this interface, which we had from the previous layer, and lift it higher, but this time into concepts that are familiar to the platform developer. So I would write another function, get face center point, and this time it's capitalized like a Java function. And the return type is actually pointf, which comes from the Android graphics package. And at this point, I expect our user to use this function. Maybe I should have made the native one private. I don't know. But now we completed this metamorphosis of our code. So we started from something extremely low level, and we reached something that is, again, very high level and uses the same terminology, the same concepts, the same type of the way of thinking of the particular system we're targeting. Now, this might actually appear somewhat contrived, the example I just shown, but in fact, most of the system APIs that you're using within Android, for example, within Java are implemented in this way. There are strongly typed wrappers around system calls that go down to the C code, the Linux running inside your phone. So this is not just some kind of nice to have abstraction. This is actually how Android is implemented. So I think it's really important. And we did this transition going from, in this diagram, it's going from left to right. And of course, the rightmost layer I show here is the application itself, which I'm not necessarily the one who's going to write it. This is my client or the team that's using our technology. And as we went from left to right, from the core business logic all the way to the app, we had to, basically, in most cases, we have to reduce our abstraction level. We have to go to a weaker type system because we need to thread through this C interface. But this isn't a compromise that we have to live with. And I've seen many libraries that do, that indeed say, OK, we have to be cross-platform, so everything is going to be the lowest level denominator, and they stick with the C, some kind of very difficult to use low-level C interface and hard to use correctly. But what I'm trying to say is that we don't need to stay there. We can continue going. And then we deliver to other teams something that gives them abstractions that they can work with and they can live with, and sometimes they're not even aware of what went on behind the scenes. And then, as I said, this isn't necessarily going to be fun. This isn't necessarily going to be easy. But it's generally easier than whatever you're doing today, unless it's generally more maintainable to do this. Because if we have a bug somewhere, it's often much easier to find it and to identify where it comes from, who is the right person to actually try and fix this, and where, and whether. And another benefit is that it helps us know what other systems this bug might manifest itself in that we haven't caught. So the lower down your bug is, the more systems it might affect. But conversely, the lower down, once you fix the bug, it automatically gets corrected on all your target systems. Now, I want to show you a small example just to make to prove to you that I'm not just waving my arms. And this is based on another blog post that I did. And how many of you are familiar with this silly party parrot? Yeah? Raise your arms? Yeah? Okay, some of you. That's a very common animated GIF on Slack, and you see it around. And I said, okay, this is a really cute animation. Let's see if we can do some actual a program that generates this from the original video, because this animated GIF is really somebody hand traced an actual video of a real parrot in New Zealand and made this animated GIF. So I said, okay, I'll find the original video and I'll try to create as I said, I'm a computer vision guy, so I decided to take the original video and try to generate a similar effect on the actual video itself. So I wrote a simple function called rotate hue. I'm not going to go into color spaces, but essentially I'm going to take each frame of the video, convert it from RGB, say, which is the normal display and color space, convert it into something called HSV. And the hue channel of this color space really controls the overall color, the hue of our frame. And I'm just going to change that hue and then convert it back to RGB for display, which is essentially what the animation does, right? So I wrote this function using OpenCV. It's an open source computer vision library. It's pure, completely C++, very cross-platform. And my function called rotate hue takes a 3-channel image. The CVMAT3B it means a 3-channel, 24-bit image, 8 bits per channel. The order is generally BGR for historical reasons, and it fills out the resulting frame after some kind of hue rotation. And the last argument is asking how many steps of the rotation I want to do, because I can control the speed that the colors are going to change, and you'll see why in a minute. And then I have some kind of a clear-all function just to make sure that I really solve my memory. Now, the example I'm actually going to show you, although most of my examples before had Windows or Android or Java, I'm going to do it in JavaScript. I'm going to show, once I had my little program running on my Windows, I said, okay, now let's see it running in the browser. Because usually when you think about computer vision, real-time image analysis or real-time image or video manipulation, browser is not the first thing you're thinking about. And since I already know how to write this kind of program, I said, okay, why don't I try, I've heard about this nifty thing, it's called Emscripten, and I managed to set it up, and I decided to go for it and try to do the same thing. So the function we saw before, this is already my C++ API. As I said, this is an example project. I don't need to separate between my first two layers or my first 3 layers, really. So this is it's a C API in the sense that they're standalone functions, and the implementation, I'm not going to show it here because it's not really relevant. And now, we're crossing into the boundary interface layer. Remember, Bill's boundary interface layer, which is cross-platform. It's platform-specific. So here we're going to write a JavaScript-ready C function that's going to pass through Emscripten and be compiled into JavaScript. Now, again, I don't want to go into to actually explain all of this code. You can read about it later. I can talk about it. But I think there are some really important things to see here, which kind of emphasize the things I'm going to talk about. So this is the boundary interface layer is where I can actually include mscripten.h, because this is platform-specific code. It's the first time we have platform-specific code. The interface needs that prefix of mscripten keep alive, and you'll note that mscripten, again, is kind of a C interface. So we need to pass the width and height of the frame, the video frame, that we're getting from JavaScript. And JavaScript doesn't know anything about 3-channel images. In a browser, when you have a video element in the DOM tree, the frames are always, they're 4 channels. It's called RGBA because you have an alpha channel. So in fact, this is, when I mentioned conversions and types, this is exactly the type of thing. At this platform, I cannot, the fact that I implemented my C interface with a 3-channel image, I need to do some conversion. So my function takes a 4-channel pointer to some data and sizes. And then I am using some OpenCV functions to do the conversions. You can see the CVT color. It converts from RGBA to BGR. I call my rotate. So the only line doing any actual work is the one surrounded by the orange square. The rest is just data conversions that are derived from knowing about my platform. So if you're not targeting mscripten, the details are not important. But whatever platform you are targeting, you must know these things. And you have to go to the documentation and find out how to do it. And the rest is just a clever way to switch around the channels to generate the outputs, right? So we have a single function that's going to go into mscripten, and we're going to use the mscripten toolchain to build what? To build a JavaScript binary, or it's an ASM.js. This code is on GitHub. Somebody actually sent me a pull request, and now there is a version that compiles to WebAssembly, which is even lower level than ASM.js. Now, remember, the BIL really was the last frontier. It's the place where we're done with C. Now we have to bring out our JavaScript foo. Okay, this is where we take the output of mscripten, and we need to integrate it into our host app. Now, what's the host app in a JavaScript in a browser? Anyone? The host app is just an HTML page, right? I mean, it's just a web page. So most of this code is related to the way data gets transferred between JavaScript and HTML and DOM elements and mscripten, because mscripten uses a different memory layout. It's the kind of details that I really ruined my slide, but I decided to put it all here just for completeness, so whoever wants to check out the slides later. Basically, I'm implementing some kind of reference counting here and managing memory, making sure I don't leak anything, but it's not really interesting. The only line where something happens is module rotate colors, right? So I pass the width, I pass the height, I pass the 2 pointers to where the pixels reside inside the DOM element in JavaScript. Again, these are JavaScript typed arrays. So we're in JavaScript land. There's no C here. This is all JavaScript. And the last argument, which is really the most interesting one, and you'll see why in a minute, is called FP color change speed. This is just an HTML element. It's a number, an integer that will be controlled using an HTML element. And all that's left is writing the actual host app. This is our HTML. This is all of the HTML files. So you can see there's a video tag, and we load the video. We display the video. This is a regular HTML thing. I didn't do anything here. And we also create, on the last line, last 3 lines, I'm creating a slider. We're using plain HTML. And this slider is going to change the value of that variable called FP. So this is what I'm going to show you is how I'm going to change the speed of the color rotation live inside the browser, so you don't think I'm cheating you or showing you a video, right? So this really shows that this is real video processing running in real time inside the browser. And right, so this is what it looks like. Let me just grab the the browser screen. Oop. Right. So what do we see here? On the left, we have the original video file. This is just a regular MP4 file hosted on in the same folder as the page. And the frames are shown by the browser. I'm not actually managing these frames. And on the right, we're seeing the video, the OpenCV processed video where I'm rotating the hue channel after the appropriate color conversion. And the slider is right underneath. And as you might expect, if I'm going to slide it a little bit to the left, suddenly the speed is 0, and you can see that it's stuck on this kind of blue-green, blue-purple tint. And if I slide it a little bit to the right, you can see that we're getting our party parrot effect, right? Live in the browser, this is C++ code. I'm not a JavaScript developer. And I think that's extremely cool. And I think that's it. Thank you. I see I'm out of time, but I'll be happy to take questions if. I don't see any, so thank you very much. Oh, yeah. Oh, yeah.
Just out of curiosity, the JavaScript but that's JavaScript, right? There's no call to the real binary?
Yes, that's Mscripton compiles Mscripton is a fork of LLVM, which compiles, somebody correct me if I'm phrasing this incorrectly, but basically it compiles anything Clang and LLVM can compile into something that's called ASM.js, which is like a subset of JavaScript, which is highly optimized by browsers. And I think the general numbers are, it runs about half the speed of the native C++ code. As I said, today there is a shift towards WebAssembly, which is even more optimized. It's not actual text, JavaScript text file. It's already kind of a binary form of the same thing, which is even more highly optimized. But yes, the original code was basically compiled into a text ASCII JavaScript representation, which it runs by the browser. Yes. OK, thank you very much.